Welcome back. We're in lesson 92. We're going to do some boat in the river problems. So when we think about boat in the river problems, we have to think about it's more than just a distance problem. It's more than just rate times time. These boat in the river problems, you have to think about the fact that you have two speeds going on. You have the speed of the boat, but you also have this current of the river. You have the speed of the river. If you think about it, picture an escalator in a department store, right? And let's say it's the down escalator. And if you're at the top up here, hey everybody, I'm at the top, and you're walking down the down escalator, well then you're walking with the speed of the escalator. You're going to get down to the bottom of the escalator. That's not a fall, I promise. You're walking. Your speed is going to be faster walking down the down escalator than it is going to be if all of a sudden you decide you want to walk up. This is down and you want to walk up the escalator. Well, guess what? You're going to have to fight the speed that is against you. You're going to have to fight the current. And it's the same thing with the boat in the river problems. You've got the speed of the river that you have to account for. Is not always going to be in your favor. It's dependent upon which direction are you going. Are you going with the speed of the water or against the speed of the water? And so there's a way we can account for that mathematically. So a downstream problem will look like this. We can already guess that it's going to be the rate downstream times the time downstream is going to give us the distance downstream, right? But the rate downstream, we're going to have the speed of the boat plus the speed of the water times the time downstream is going to give us the distance downstream. So this is the formula we're going to look at right here. Now, what if you're fighting upstream? Well, if you're fighting upstream, then every mile per hour that the water is flowing against you is going to subtract from your speed. So the rate upstream times the time upstream is going to give you the distance upstream, but you're going to be at a little bit of a handicap. And the way we do that mathematically is we say the boat minus the speed of the boat minus the speed of the water times the time upstream is going to give us the distance upstream. So this is the formula that we use for an upstream problem. Okay, so let's apply those. Put those in your notes, and let's apply those to our first problem, 92.1. All right, Robert and Clay could go 60 miles downstream in the same time it took them to go 20 miles upstream. If the speed of their boat was 8 miles per hour in still water, what was the speed of the current and what were their times? So let's apply our downstream equation. So we know we have downstream is going to be B plus W times the time downstream. And downstream, we know the distance downstream is 60 miles. So let's put 60 in here. And now we're going to do the upstream. And the upstream is going to be B minus W times the time upstream. And we know that that is 20 miles. Now, it says in the same time it took them to go 20 miles. So the time is going to be the same. So instead of having a factor TD and TU, we know that TD is equal to TU. So let's just use T to represent all the time since it's the same value. So we're going to say B plus W times T is equal to 60, and B minus W times T is equal to 20. I just like to have the one that's being multiplied or distributed in front. That's just, it's, the commutative property, so it doesn't matter. So that gives us TB plus TW is equal to 60, and TB minus TW is equal to 20. So now we need to put in the value of the mileage of the boat. So the boat speed was 8 miles per hour. So we can substitute that in here pretty easily. We'll put that in for B. So it's going to be 8 times T plus TW. Whoops, make that look like a W a little bit better. Equals 60. And 8T minus TW equals 20. So when you have these two variable problems, the easiest way to take care of them is to treat them with either, or to solve them with either substitution or elimination. We're going to use substitution since we have a plus TW and a minus TW. That's going to be the easiest way to do that. So I'm going to rewrite those over here. 8T minus TW is equal to 20, and 8T plus TW is equal to 60. So when we combine those to eliminate, and we get 16T is equal to 80. So when I divide both sides by 16, I find that T is equal to 5. So 5 hours is the time. So now that we have the time, we can substitute that into all of our problems. So I'm going to say here I have 8 times 5 plus 5 times W equals 60. So 40 plus 5W is equal to 60. So that tells me I can subtract 40 from both sides. 5W is equal to 20. W is equal to 4. So the speed of the water is 4. All right, so now we can use that to solve for their times. So the upstream time is the boat plus the water. So the boat is 8, the water is 4, and the time is 5. All right, so the rate for the downstream is going to be 12 times 5, and that is indeed 60. And then for upstream, we have 8 minus 4 times 5 should equal 20, and indeed 4 times 5 is equal to 20. So the downstream time was the downstream speed was 12 miles per hour, and the upstream speed was 8 miles per hour. All right, so let's look at 92.2. All right, 92.2. The steamboat Juby Fountain could go 70 miles downstream in 5 hours, but required 6 hours to go 48 miles upstream. What was the speed of the boat and the speed of the current? So we'll begin by writing both of the equations. Here's the downstream equation. We have the boat plus the water times the time downstream is going to equal the distance downstream. And boat minus water times the time upstream is going to give us the distance upstream. Next, we are going to replace the distance downstream, the time downstream, the distance upstream, and the time upstream with the information from here. So we have the boat plus water. This is our rate. And the time is going to be 5 hours. That's the time downstream. That's right here, in case you're looking. And the distance downstream is right here. That's 70. All right, so now we have boat minus water, and the time upstream is going to be 6 hours. And the distance upstream is 48 miles. And that's going to be 48 right here. So now we're going to do a little bit of distribution. Since we don't have any values for the boat or the water, we're just going to distribute this. We're going to say 5 times the boat plus 5 times the water equals 70. And 6 times the boat minus 6 times the water is equal to 48. Now, you and I both know that we have to have a number that is going to allow us to use elimination. So we're going to multiply both of these by the opposite coefficient. So I'm going to multiply this one by 6, and I'm going to multiply this one by 5, and I'm going to write them here in the middle when I complete them. So this is going to be 30b plus 30w equals 420. And then 5 times that, that's going to be 30b minus 30w is going to equal 240. So we're going to combine those. We're going to eliminate these two. And we get that 60b is equal to 660. So we divide both sides by 60. And b is equal to 11. So now that we know what b is, we can go in and we can substitute into both of these and find out what the speed of the water is. Or we can just do one and find out what the speed of the water is. So let's do this one on this side. So the boat is 11. So 11 plus the water times 5 is equal to 70. So 55 plus 5w is equal to 70. We subtract 55 from both sides. We find that 5w is going to be equal to 15. So the speed of the water is 3. So the water is 3. The boat is 11. All right. So whenever we have the boat going downstream, we have 11 plus 3, which is 14. When it's going upstream, we have 11 minus 3, which is 8. So those are the speeds of the boat and the speeds of the current, and these are the two things we had to solve for. All right, let's look at 92.3. This is our last one. All right, 92.3, this is our last problem. The water in Flint River flows at 5 kilometers per hour. A speedboat can go 15 kilometers upstream in the same time it takes to go 25 kilometers downstream. How fast is the boat? So first of all, I see in the same time it takes. So we know that the time upstream is going to equal the time downstream. So we can use that same t for both problems. So now we are going to say, we're going to write our equations here. We're going to say b plus w times t that is our downstream. That's 25 downstream. And our upstream is b minus w times t, and that's 15. So now let's sub in our speed of the water. So we have b plus 5 is t, and that's 25. And then b minus 5 times t is 15. So now we'll distribute. We have tb plus 5t equals 25. And then we have tb minus 5t equals 15. So now we can just do a little bit of elimination. So I'm just going to bring this one over here. And I'm going to say tb plus 5t. I don't know why I wrote 52. 5t is equal to 25. So I draw my line. These cancel. So I have 2 times the boat. 2 times the time times the boat is equal to 25 plus 15, which is going to be 40. All right, so now I am going to divide by 2, and I get that the time times the boat is equal to 20, which doesn't tell me anything. I still have the time times the boat. I don't know how fast the boat was going. So it looks like we made a mistake in the way we solved it, or in the way I solved it. And I did it this way just to show you that you don't always use the negative and the positive that you're given. So here's how we actually need to solve this problem. I'm going to take this off, and I'm going to rewrite it for us. This would be TB minus 5t equals 15. So instead of using what is already given to us to eliminate, we have to think about our problem first. If we use TB and say 2TB, we have an unknown times an unknown. If we have two unknowns, we cannot solve the problem. As you can see, we end up with a number that we can't we know what the factors are. We know 4 and 5, 2 and 10, 1 and 20, but we don't know which is which. We don't have anything to go by. So what we have to do is depend upon the term that only has one unknown, and that's going to be the 5t. So what we're going to do instead is we are going to multiply this one times a negative 1, because we need to get rid of the TB so that we can figure out what t is. And then it's going to give us negative TB plus 5t equals negative 15. Now we can take this one and bring it over here and say TB plus 5t is equal to 25. Now this cancels, and we have 10t is equal to 10. So t is equal to 1 because we divided both sides by 10. 10 times 1 is 10. So our time is 1. Excuse me, I'm talking too much. So now we have our time, but that doesn't tell us how fast the boat is. So now we need to sub this in to figure out how fast the boat is. And I'm just going to take this one right here and sub it in. So if t is 1, 1 times b is b, and 1 times negative 5 is still negative 5. And that's going to still equal 15. So if I add 5 to both sides, the speed of the boat is 20. So now I know how fast the boat is. All right. And if you want, you can sub that back into the original problem, and you can say 20 plus 5 times 1 is 25, and 20 minus 5 times 1 is 15. And so you get the same answer. Everything checks out. You know you've gotten the right one. So think about whenever you're working a problem and you have the situation where you have two variables together, you have to solve or eliminate the one that has the two variables. Don't just go for the easy one that's already negative and positive. You have to look at what you have and think about, can I get an answer from this? If you get stuck, just like we did in this illustration, go back to a point before you decided to eliminate and multiply one of them by -1, and that'll help you get over it, just like we did here. So that's how you would resolve that issue without having to start all the way back at the beginning. And that's all we have for lesson 92, and I will see you in lesson 93.